Good morning, one and all. Join the meeting fast. Okay, so good morning, one and all. Today we are going to see the next bit of our chapter, and that is Yeah. And that is um, designing elastic, highly available, and resilient infrastructure for varied application scenarios on AWS. Okay, so these bits like elastic, highly available, and resilient infrastructure we are going to see in case of AWS, then Microsoft Azure, and Google Cloud platform also. But today we will start it with AWS only. So let me share my screen. Mhm. Yeah.
Hello and welcome to the Rackspace Fanatical Support for AWS webinar, AWS Best Practices Designing Scalable Architectures. Good morning or good afternoon, depending on where you're joining us from. My name is James Cow. I'm the Director of AWS Strategy and Architecture at Rackspace, and I'm joined today by Jerry Hargrove, one of our Senior Solutions Architects specializing in AWS. Just wanted to thank everyone for joining us today and taking the time out of your busy days to spend an hour or so with us talking about these best practices. We're all aware that AWS provides many services and products that are designed to help us take advantage of the benefits of running scalable workloads in the cloud. But really knowing how to utilize these services to build both fault-tolerant, highly available, and most importantly, cost-effective applications and workload architectures is something that often requires a lot of expertise or experience in using those products and services. And it can be quite hard to find that expertise. So during this webinar, myself and Jerry are going to tap into over 15 years of combined AWS experience between us to outline some of the common design patterns or best practices that you would typically need to use when you start addressing architecture at a scalable and cost-efficient level on AWS. So at this point, I'm going to turn you over to Jerry Hargrove, who is going to introduce himself very briefly and then start the presentation for us. If you have any questions, please just drop them into the chat window during the presentation. We'll either try and answer them at the end of each kind of section, or maybe we'll take more Q&A at the end if there are a lot of questions. Jerry, over to you.
All right, thanks, James. I appreciate the introduction. Very quickly, as James mentioned, I'm a solutions architect with Rackspace. I focus on AWS. I've been working in AWS for about the last 7 years. What we're going to talk about today are some best practices around scalability and talking about some of the benefits of scalability in the cloud. If any of you have ever been to one of the AWS summits or reInvent, you've probably seen a slide, something a little bit like this, where Andy Jassy or one of his representatives gets up on stage and starts talking about some of the benefits of cloud computing. And it usually goes like this: you can replace your capital expenses with operating expenses and stop paying that money up front. You can, by moving to the cloud, you can lower your overall costs by leveraging some of the economies of scale that AWS provides you at their scale. You can stop guessing capacity, and this is what we're going to talk about today, and I'll come back to that shortly. You also, one of the benefits of moving to the cloud is just the agility and speed and innovation at which you can innovate and you can move on the cloud. It allows you to move very quickly from one product to another, from one iteration to another, and allows you to focus on your product and the aspects of your product that differentiate yourself from your competitors, and not focus on the actual infrastructure that's underneath it. The final benefit is the ability to just go global in minutes. So once you move to AWS and you've got your application running in the Oregon region, you can literally be up and running globally in a matter of minutes, moving it to a region in Ireland or in Australia, wherever you'd like to be. It's that quick. So what we're going to talk about today is this third bullet item here, stop guessing capacity, and really how that relates to scalability. So I'm going to jump right into it and get started. What we're going to cover today are, at a very high level, some key concepts around scalability in the cloud and best practices around scalability. And we're not going to talk really much about horizontal scalability or vertical scalability, but some other concepts. We're also going to talk about cost and scalability. So what does the scalability cost you? Also, we're going to look at some aspects of developing for scalability in the cloud. And finally, operating at scale. So what are some of the best practices that you can adopt to operate in a truly highly scalable environment? And as James mentioned, depending on timing, we'll either take questions in between some of these sections or we'll hold and we'll answer questions at the end. So I'm going to go ahead and get started. So the first thing we're going to talk about are some just high-level concepts around scalability in the cloud. And one of the first things that we usually talk about is this idea of having the ability to only have the amount of content graph here. I accommodate those very quick. One is not instantaneous, and bring another one in its place. And I'll talk a little bit later. Depending on servers was experiencing problems, we would spend the time and the money to repair it and bring it back into operable condition. We'd nurse it back to health when it wasn't doing well, just like we would do a pet. We would take it to the vet, we'd make sure that it got all the medications and the treatment that it needed, and then we'd bring it back home.
Will be
in the cloud and in a
light
truly
on
scalable environment where
repairing
our
and
resources
replacement
can
in
come
case
and
of
go
changes.
depending on demand, or perhaps they even fail, we take a little bit of a different view of this, where we think of them, individual resources, as part of a herd, and with no one member being any more important than the other. And in this diagram, it kind of demonstrates, if one member of our herd fails or is no longer performing, we simply replace it with another one, and in this case, we put that one out to pasture. And this makes sense. If it's a web server fleet that we have running and maybe we have hundreds of instances, we simply take a failing instance out of rotation and bring another one in its place. And I'll talk a little bit later about some of the implications of that, but in general, that's the approach that we have to take in a scalable environment. One of the other things to think about in a scalable environment is state. And oftentimes when we're talking with customers about building out super scalable environments, we ask questions about what kind of state is maintained on this system. If you have an application tier and you want to make it super scalable, we need to think about what state is maintained on that system. And that state can come in many different forms. It can come in the shape of a file on disk. It can be a database. It could be images or files or media files uploaded by users. All of those constitute state on our system. They are things that we would need to recover in the event a system failed. And a good example of this, a fairly common example of this, if you think about a web server tier, is session state. So imagine a case where a user logs into your system, they go through a load balancer, and they're directed to one of the instances behind that load balancer that's handling web traffic. Maybe you have tens or hundreds of these servers up and running. When that user logs in, they're directed to an available web server based on some load balancing policy, and their session info is potentially stored on that web server. And so then the end user makes subsequent requests into that web server, and they're redirected back to that same web server that has their session state, and they can go on and on like this, so long as they're going back to the same server. Now, in the case of a scalable environment, some of those servers may come and go depending on the demand on the system. And in this case, it's demonstrating what happens if the web server that user is currently going to disappears. Well, in this case, if we're maintaining state on the server, all of a sudden that session state disappears, and then the user ends up either having to log back in again or potentially losing any information that was stored in that state. And in some cases, it may simply be an inconvenience. In other cases, it may mean that the user loses some work or some data that they're working on. So anytime we're talking about super scalable architectures, we always want to know where state is maintained in the system and come up with alternatives for that. In this case, we may want to store session info in a distributed memcache caching store. We may want to put data files up in S3 or on a shared file system, and databases, of course, in RDS, but thinking about those things. I'll switch gears then and talk a little bit about associated cost, and talk a little bit about what some of the things are that we can do to address cost issues or cost implications of running in scale in the cloud. And so first, let's talk a little bit about right-sizing our system. Right-sizing is what we do when we're trying to match our capacity to our demand at a more granular level. And this really a lot of times comes up when we're talking about matching EC2 instances to a current application. And right-sizing is really about choosing the right instance. And a lot of it depends on the information that you currently have. It usually depends a lot on where you are in your development and product cycle, what information, where you're coming from, what information you have about your workload. So say, for example, you are moving an application to AWS and you're trying to optimize your choice of EC2 instances. If you're moving from an environment where you currently have this application running, whether it's in a dedicated or you're in a colo and you have servers running already, you have some idea of what the capacity requirements are for your applications. You're running on a 4-core server and you've got 32 gigs of RAM. That gives you a great starting place to decide on the EC2 instance that you're going to use, with the caveat that you probably over-allocated that dedicated instance to deal with some capacity issues later on down the road. But that gives you a good starting place to start with. But oftentimes we don't have that information, or we're just making a guess. And so the first thing we want to do is try to characterize our application and put it into the right bucket, if you will, on AWS. So what EC2 instance type does this map to? Is your application CPU heavy? Is it I/O constrained? Does it require a lot of memory? All of those things will help you decide on the type of EC2 instance that you want to start with. This gets us in the right ballpark to begin with. And as my simple example here shows, you don't want to choose a bus when really you need a small sports car. If you're a small family and you got one pet, you really don't need a bus to carry you around. At some point you may need that capacity, but you currently don't. So let's go ahead and pick an instance type and size that's appropriate for your workload. Now the nice thing about working in AWS and working with this infrastructure is we don't have to get it exactly right on day one. If we build out a scalable system that allows us to scale on demand elastically, then even if we're a little bit off on our selection of EC2 instance type, our system will scale up and down to meet that demand. Getting the instance type dialed in is usually not something that happens on day one. That over the course of time we'll continue to refine that and continue to dial that in. So long as we build out a scalable system, we're okay. Sometimes it may feel like when we're choosing an EC2 instance that we're throwing a dart at a dartboard, but a lot of times that's okay. As long as we get it in the right section of the dartboard, we're okay. We can continue to refine in after that. The next topic around cost usually comes up when we start thinking about reserved instances. Now, if you're unfamiliar with reserved instances, this is a mechanism that AWS provides to AWS customers that allows you to essentially indicate that you're going to want to use this particular EC2 instance type for a period of time, or RDS instance. There are a couple of different cases here. That you're going to want to use it for a particular period of time, and in return for doing that, AWS gives you a significant discount on that EC2 instance, and depending on the term that you require, whether it's 1 year or 3 year, and the instance type, you can see from 30 to, I've seen up to 75% savings over the course of a reserved instance lifetime. Now, a typical use of reserved instances, and I'll talk about what's in the graph here, is you have a particular workload, and you see your demand over time has established a baseline, and that's seen here below the dotted line in this graph, that you see a baseline of demand that you want to reserve capacity for. You know that you're not going to go below that, and that's a good case for reserved instances. And so you purchase reserved instances that are sufficient for that particular demand. And above and beyond that, you continue using on-demand instances. So you have reserved instances that are there for you to meet that that constant demand, and then you use on-demand on top of that, just like you normally would. Now, some people go even further than that. I think Netflix is a good example where they actually reserve all of these, and those peaks and valleys you see in the on-demand section here, they actually establish their own spot market internally within their company, and allow other groups to use that. One of the questions that we see very often about reserved instances is, should I purchase reserved instances on day one? I really want to realize that cost savings. And oftentimes the answer to that is probably not, that you should usually wait, and maybe that's a month, and just make sure that you're choosing the right instance type. There are some restrictions when you buy reserved instances. They're associated with particular regions, and in some cases availability zones and families. And so once you choose one, you end up having to use that instance for the duration of that. Now, AWS has recently introduced some more options around flexibility that allow you to convert your reserved instances to other types over the course of time. It used to be much more difficult to do that, but now you can change your reserved instances with a little more flexibility. So in addition to reserved instances, there's another way to purchase capacity in AWS, and that is through the use of spot instances. So you have on-demand, which is capacity that you can purchase on an hourly basis. You have reserved instances, which allow you to essentially purchase capacity over a long term and achieve a significant savings over the course of that reservation. The third way you can buy EC2 instances and compute resources is through AWS's spot instances. And if you think back to sort of the typical demand, the cyclical demand graph, where you have your weekly cycles or monthly or business cycles, and you have this very high capacity, say on Black Friday, or very high demand on Black Friday, and throughout the rest of the year you have lower demand, you have all of this excess capacity. What AWS does with that excess capacity is they sell it back to us, in this case in the form of spot instances, and those are EC2 resources that currently aren't being used, and you can buy them essentially for pennies on the dollar. You bid for those resources with other AWS customers, and so if you say, for example, you need an M4 extra large instance and you want to bid for it on the spot market, you place a bid for that. If your bid is higher than other AWS customers, you'll get those resources. However, if another AWS customer comes in after the fact and outbids you, those resources could go away. So I want to talk about that just for a couple of seconds. So in the example I'm showing on this slide, this is a pretty common one where you have a set of users who are using some particular resource and they're submitting requests to your system. And in the upper track, those requests are queued up, and you have a back-end system that scales based on the depth of that queue. So for say this was a premium customer who paid for your service, you might have a set of reserved instances that were handling the baseline demand on your system, and then have on-demand instances scaling up and down to handle additional requests. As queue depth grows, you would add more on-demand instances to handle those requests. And so you have this sort of normal scalable system based on queue depth. Now what happens if you wanted to offer maybe a free model for some of your customers, a freemium type of approach where you allowed them to use your system with low or no cost, but you wanted to save money on your end? You could implement a very similar model as shown in this diagram where you use spot instances to handle those requests. So from your free customer's perspective, the system might not be as responsive, or they may have to wait a little bit longer to get their request processed. But on the back end, you would save money by using these spot instances. Now, one thing to note about the use of spot instances, as I mentioned earlier, they can come and go fairly randomly. So if another AWS customer bids on those same resources and outbids you, those resources, those EC2 instances, can go away. And so you need to make sure that the work that those EC2 instances are doing, those spot instances are doing, is either idempotent or can be recovered or is resumable. So a good example of that would be maybe you had a service that was resizing images or watermarking images or something like that, making sure that you could restart that process if the EC2 instance that it was running on for whatever reason was no longer available. In this case, it was a spot instance that was you were outbidding on. But I want to stop for just a second here. It looks like we have a couple of questions in the queue. I'll see if I can answer them. One of the questions is what is a good approach to securing your scalable AWS cloud environment? I don't talk a lot about it in the slide deck, but security is one of the other attributes as a solutions architect that we look at when we're talking with customers, is what mechanisms are in place to secure this environment. And it depends a lot on the application and the customer itself. We'll utilize whatever AWS services and features are available using particular IAM roles, identity and access management, establishing users and roles to control access into this system, so that access into EC2 instances or the permissions that those EC2 instances actually have to access other AWS resources and services is utilized. You can also utilize data encryption both in flight and at rest, so you can establish secure connectivity between EC2 instances inside this environment and other services. You can use ELBs to terminate SSL connections at the front end of these environments. You can use encryption of EBS volumes on EC2 instances to secure those volumes. We actually have a security white paper that's been published. I will go ahead and provide that link to everybody so you can take a look at it and read it at your leisure after this. One other question is around applications that are designed not to scale, and I'll see if I can address this question. So oftentimes we do see applications that are, perhaps it's a commercial off-the-shelf application that you have running and you want to move it to the cloud, or it's some legacy application that is not cloudy and you want to move it to the cloud. Unfortunately, you can't or you don't want to ever have more than one of those instances up and running at the same time. This could also be because of licensing reasons. You only have one single license. So you can't really make that scalable other than scaling it vertically. So you can scale vertically by moving from one EC2 instance size to another. For example, you start with a C4 large instance, and you decide you need additional capacity, so you move to a C4 extra large or C4 2 extra large, and up the ladder until you reach the top. That is how you would scale that particular instance or that particular application in this environment. Now, there are other questions around availability. I haven't really mentioned it, but one of the things that we also get when we implement a scalable environment usually is a highly available environment too, because we're able to scale out horizontally. We now have some redundancy in our system. And in the case of a singleton application like the question was around, you really don't have that redundancy. And there are other mechanisms to put in place to ensure or to minimize downtime in case there's ever a problem with that instance. So I'll move on to the next section, and this one focuses a little bit on development. And I come from a development background, and so these are some of the things that I've learned over the course of time and some best practices that we've established at Rackspace for working with developers who are developing applications for the cloud. So I want to start with one thing, and there are actually two components to this. There's logging at scale and also monitoring. And unfortunately, I don't have anything here on monitoring, but I'll try to bring it up as well. In a distributed environment, regardless of whether you're scaling or not, but in particular in a scalable, elastic environment that's distributed, logging is a critical and key component in this environment. It's one of the building blocks for building a maintainable, manageable, supportable, scalable application in the cloud. And the reason for that is really this. If you look on the right-hand side, and I hope this is large enough for everybody to see here, in this scalable environment, if we have tens or hundreds of servers running in an environment, say it's a web server, for example, that's a good way to explain this. If there's a problem with one of those web servers, and thinking back to our pets versus cattle analogy, if there's a problem with one of those servers, we don't bring it back to life. We don't try to nurse it. We don't triage it. We don't try to repair it. We simply take it out of rotation and bring another one up in its place. And when we take that instance out of rotation, in this case, it's it could be a system failure. It could actually be a scaling event. Once that system is taken out of rotation, it no longer exists. Any logs that were stored locally are no longer there. Any metrics that were stored locally are no longer there. They're gone. And so in a distributed environment, if we want to log, we need to move those logs off of those systems as quickly and as soon as possible. And so we start looking at logging infrastructures. And in order to do that, we want to make sure we have a logging infrastructure that is reliable, that it can survive in the event of networking issues, network partitions, slowdowns, that it's capable of accommodating spikes in traffic, that it's capable of very high throughput, and it's also capable of low latency operations. Now, this starts to sound like a typical service in the cloud, and it really is. Logging becomes a tier 1 service in our application, and you start to see applications like in the lower left here, where we build up services that have agents installed on them. And in this diagram, the little A in the box is an agent, and that agent is responsible for shipping logs off of that instance. So in the web server example I mentioned, HTTP logs, access logs, error logs, all of those should be shipped off of that instance and aggregated in some central repository. In this case, the agents on individual systems, they send those, they take those logs and they send them to a source aggregator, and that source aggregator then sends them to a back-end logging service, which may have a load balancer in front of it for load balancing across multiple instances. This particular design pattern has a scalable back-end where target aggregators can then scale in and out based on demand, just like a normal application would, and then store them in a highly available, durable database. And so the actual logging architecture looks like any traditional application architecture in the cloud. And I wanted to mention that, you know, along with logging, we also need to consider monitoring. And that really means the same thing, that once these systems go offline, once they're taken out of rotation, that information is no longer available. So we do things like instrumenting our code, aggregating our metrics, and shipping them off to a metrics aggregation service. And you know, I'll mention here because they're fairly easy to use. That would be, you know, CloudWatch on AWS. In terms of logs, you could also send these off to your logs off to CloudWatch logs to aggregate them, and then be able to query them later on if there is a failure and you want to go back in and triage, do some forensic analysis of your logs. You can do that because once that instance is gone, it truly is gone. One other thing that I want to talk about at the developer level is around resiliency and fault tolerance in the cloud. And I don't call it out here, but Werner Vogels, who's the CTO of AWS, he has a very famous quote, at least within the AWS circles, is everything fails all the time. At some point, every component in your system is going to fail, and you need to plan for that. And I call it, you have a date with failure. It will happen in your system at some point, and you just don't know. You don't know when it's going to happen or where it's going to happen, what level it's going to happen in, the extent of it, or how long it's going to take. What you can do, though, in the face of that uncertainty is you can plan for it. And that's really the point here, is that we need to start thinking about our applications and our application stacks in terms of failures, and identify those single points of failure within our system, and understand and plan for what types of actions we're going to be able to take. We need to look at it from the top down, starting at really at the DNS layer. What happens if your site is unreachable? So say you have an external service that you're using to ping your site, and it responds with a failure, or your site is unreachable. What are you going to do? Do you have a failover strategy in place such that your users just don't see a blank screen, that your site is unreachable? How are you going to address that? Moving down the stack a little bit, what are you going to do if a web server fails? How are you going to handle that? You know, and in a scalable environment like we've been talking about, that buys you some level of high availability, and so we use that to our benefit, such that if an EC2 instance fails in our scalable environment, we use auto-scaling groups to automatically bring another one back up in its place. What happens if an availability zone in AWS fails? What's your strategy going to be there? We always architect solutions that span multiple availability zones. What happens if our systems can't scale fast enough? What are we going to do in that case? Now, I bring this up because oftentimes these failure cases aren't strictly binary. It's not simply it works or it doesn't. We need to be thinking about that gray area in between and think about alternatives. Can we degrade our service instead of simply failing it and not operating it? Other questions as we move down the stack are, what do you do if your caching layer is unresponsive? How do you handle that? Instead of just falling over, do you simply go directly to the database in that case? So we want to make sure that our systems are designed and built and coded to not be so brittle that they don't have a recovery path in case some of these failures happen. Even in the case of a database failure, what do you do in the case your underlying database fails? Well, you may be able to degrade into read-only mode, for example. Just thinking about all of those, looking at all of those points in your system and identifying what the failure points are and what your action is going to be when that does happen, and making sure that that's codified in your application and that you have strategies or processes in place to deal with that when it happens. One of the things I like to call out too is occasionally there are outages on AWS, and usually we hear in the next day or two of different AWS customers who have had problems and whose customers couldn't reach them. What you don't hear about, though, are those customers who didn't have problems, who designed their systems to be fault tolerant and resilient and didn't have an issue with an outage of one particular time. And that's really where we want to get. We want to get to the point where we're not newsworthy in the event that there's any type of outage or service disruption on AWS. That from our customers' perspective, it's business as usual. The third thing I'd like to talk is just a little more detail around defensive development and how we can code defensively in our applications to handle some of those failure points. One of the things that we want to do is we want to plan for problems, and we want to plan for problems and have code in place to deal with those as if they do come up. And some of the common strategies, and I want to cover one design pattern here today, is the circuit breaker design pattern. And just to cover it real briefly, imagine you have a client and server application, and we can go back to the previous slide where we're talking about, say, for example, the caching layer. I have an application that utilizes our caching layer and to get data, and if that data is not present, then it goes to the server to obtain that data. What happens in the case that that caching layer becomes unresponsive, as was the question in the previous slide? What if we start seeing timeouts at the caching layer? What do we do? Well, what happens a lot of times if there's no strategy in place is those timeouts start building up, and so you start seeing errors in your system, and you start looking at graphs, and you start seeing activity that's taking exactly 60 seconds, if that's the timeout value, to occur. Those timeouts start backing up, and that timeout starts bubbling its way back up to the top of the system, and you have this sort of cascading failure of your system. The circuit breaker is a design pattern that's intended to mitigate some of that effect. So it actually monitors that request from client to server, in this case from cache client to the actual cache itself. And if it starts seeing errors like timeouts occur, and it may use a simple metric like the number of times this occurs, it may shortcut that. It may trip the circuit breaker and say, okay, for the time being, we've seen enough of these. Let's go ahead and redirect all requests directly to the database. Now, that means potentially that latencies are a little bit higher for your customers while there's a problem, but they're not timing out. They're not seeing that 60-second timeout that they were seeing before. And then the circuit breaker, all requests continue to go through the circuit breaker and they're redirected to the server itself, but the circuit breaker occasionally tests that connectivity again in an exponential backoff type of form where it waits a couple of seconds, a couple more seconds, and then that continually grows. And when it detects that it's back to business as usual, it will start redirecting those customers back to the cache in this case, or whatever the server was. And so it's a case where it's not simply a failure or success, but let's do something that provides a good customer experience without completely failing it over. And the example I give it sort of in the lower left here is it's very common to see this in code where you have a try block, you catch everything, and you do nothing. You completely mask it or ignore the error. Instead, we want to do something like we want to try some operation. We want to catch something specific. In this case, it's a timeout condition when they're trying to reach the cache. And if we detect that, then let's go ahead and degrade that service, and if possible, such that the customer experience, while not perfect, while not optimal, is still a good customer experience, although somewhat degraded. So I'll go ahead and look real quick. I think I have time for maybe one question in here. Let's see. There's a question about spot instances from the last section about when could I use spot instances knowing it's a risk someone may outbid my resource. And that really goes back to what types of jobs you're doing with those spot instances. I mean, generally, you can save a significant amount of cost by using spot instances, but you have to realize, as was mentioned, that those spot instances can disappear at any time. So you want to make sure that the jobs that those spot instances are performing are resumable. So you want to make sure that if you have a spot instance that is running for 45 minutes and doing a particular job, if it stops at minute 46, that you don't necessarily lose all 45 minutes worth of work that you've done. So you want to make sure that those jobs that those spot instances are working on you can resume them, or you can very easily redo those jobs to make sure that they're immutable. Other questions, let's see, cost estimation tool around the use of RIs, etc. There are a lot of estimation tools that allow you, either third-party tools. Our Rackspace Compass tool also provides guidance around when to look at the use of RIs. So if it notices that you have a constant demand on systems, then it will make recommendations on RIs. Typically, as I mentioned, it ends up being you have a steady state capacity requirement in your system that you don't expect to decrease over time, that it will be there and not go away. All right. We'll have a couple more questions. We'll try to get back to those as we near the end. The last section I wanted to talk about here is around operations and operations in a scalable environment. And this kind of goes back to sort of the whole DevOps model, although it's not just a DevOps thing, and that is automating all the things. The DevOps model, I mean, just in general, when we get to the point where we have a truly scalable environment, we want to automate as much of that environment as possible. We want to automate the introduction of new instances into the environment. We want to automate deployment of code to these environments. We want to automate development, the development processes in these scalable environments. If you think of sort of in a smaller environment, or perhaps in a development environment, it might be very common for individual developers to, say, for example, SSH into an individual instance, update the code on it, and put that instance back into rotation. When you get to the point where you're operating at scale and you've got tens or hundreds of instances running at the same time, that's no longer an option. That really isn't feasible. So you have to have some mechanism in place, for example, to automatically deploy code, and you have to have some form of continuous integration and continuous deployment mechanism or tool set in place to automate that. As is true, with the DevOps evolution, or the evolution of DevOps, we want to evolve our practices. We want to evolve the mechanisms that we use. We want to evolve the tooling that we use to work in this environment, to make sure that we're taking advantage of all of the services and features that are out there. And lucky for us, AWS provides a lot of those mechanisms for us. They provide tools like Code Pipeline, Code Deploy, Code Commit that allow us to automate this process so that we can truly move towards this, break down all these silos between the different groups and organizations that we're parts of, and move to this environment where we are continuously improving our product, continuously improving our process. We're no longer synchronously handing artifacts, build artifacts over to new teams or test environments over to other organizations, that we move to an environment where we're all working together as one team and continuously improving. One of the questions that comes up quite often is, and I mentioned earlier, is deployment model. So in this environment where we potentially have maybe hundreds of instances running at the same time, maybe tens of application layers, we've got web servers, maybe we have organized our architecture in a microservices fashion where we have tens or hundreds of individual services. How do we automate deployment to those environments? How do we manage that at scale? And like I mentioned on the previous slide, we automate everything. We want to automate all the things. And we really want to do it in such a way that we are able to produce a repeatable, predictable behavior in our system. And as part of that process, we want to try to minimize interruptions and downtime. And there are several ways of doing this, and I don't call them out here on the slides, but there are several mechanisms in AWS that we can use to deploy code. Code Deploy is one obvious choice just because of its name. It allows you to automate deployment of your code. You can do a rolling deploy out to your environment and update code in that way. You can use other tools if you're using tools like Capistrano, or there's tools like Webastrano or Octopus on Windows. All of those provide automation capabilities and integration into AWS. One deployment model that is fairly popular and we see quite often, and many of you may be familiar with it already, is a blue-green deployment model. And that really is the diagram in the upper right demonstrates, as opposed to doing a rolling deploy where you are sequentially updating individual EC2 instances, for example, with the latest code, you actually stand up a separate stack and make a switch over to that new stack, and that it's termed blue and green. Blue green stack, which you then switch over to. And there are a couple of different places talking specifically about AWS where you could do that switch over. One is at DNS, you could build a new stack and simply update it to point to the new ELB. You could use DNS to do that. You could swap out the ELB. You could swap out individual EC2 instances, or you can do the switch at the auto-scaling group. And in this case, best practice is usually around the auto-scaling group, simply because there could be DNS TTL issues. And I can answer questions about that later. But this is a very, very common approach and used in a lot of environments, big and small, microservice environments, containerized environments as well, one that we commonly see and recommend for customers on a fairly frequent basis. One other question that we very frequently get is around the use or how to build AMIs. And it's probably one of my favorite questions to answer and to talk about. And I won't go into a whole lot of detail. There's a lot of detail on this slide, but AMIs are the machine images that you use to run an EC2 instance. So it's an image that contains, at the very basic, the operating system. And a lot of the machine images provided by Amazon are just that. It's a base operating system. It's Ubuntu, or it's Amazon Linux, or it's Windows. And then you build on top of that. You can install your application dependencies, your application itself, and the configuration associated with that application. And there are different ways of deploying or using that AMI in AWS. In a scalable environment, you can use, as demonstrated sort of in the lower right-hand corner here, a basic AMI, which consists mainly of just those foundational components, and then at runtime you bootstrap your instance. When the web instance comes online, it has the operating system. It goes out and downloads the latest dependencies, gets the latest source code from GitHub, and then gets the configuration. Once it has all of that, it is then able to start taking on web traffic. And so that's the very basic model. It's super flexible because all of this is generally scripted, and so you can change that scripting very easily. As you can imagine, though, if this were in an auto-scaling environment and you wanted to bring this instance up very quickly, it could possibly be slow because it has to download all of that and configure the instance. On the other end of the spectrum, you have a baked AMI, which is essentially a golden image that you have everything already pre-baked onto it. So you have the operating system, your dependencies, all of your applications, and configurations, such that when a new EC2 instance is started up in your auto-scaling group, it is immediately able to start taking traffic. So this is the fastest route to take. It's the least flexible, though, because anytime you have changes to your environment, you have to bake a new AMI. In the other case, the basic case, you don't necessarily have to create a new environment. You just update scripts. More often than not, what we see from customers is sort of a hybrid approach here, where you create an AMI that you're going to use. You bake in all of those things that change infrequently, such as, of course, the operating system, any applications or frameworks that your application uses that don't change very often, and use that. And so in an auto-scaling group, when this instance is brought up using this AMI, all it has to do is go out and get your latest source code and configuration, and it's ready to run. So it's a good compromise between the basic and the baked EC2 instance, and provides you the ability to, number one, get something that's fast, and gives you some flexibility then in what you put on it. The fourth item I wanted to talk about under operations is just tools, and so tooling. And I apologize, this slide is probably an eye chart for everybody, but really the point here is there are a lot of tools out there that you can use to help automate your environment. Everything from continuous integration tools, continuous deployment, code repositories, all of these falling into sort of the infrastructure as code, trying to build this out so that we can build these automated environments that allow us and allow our developers to develop code, to have that code automatically deployed, to have it tested and integrated, and then moved out to our staging and production and test environments in as automated fashion as possible. So again, a big eye chart on here. There are lots of tools out there. I encourage anybody who's going down this path to start looking at these tools and start thinking about how you're going to use these tools in your environment from day one. So that's really it for me. I want to do a quick wrap up. We talked a little bit about some ideas, some key concepts around scalability, some best practices around costs, the things that you can do to optimize costs in your environment. Also talked about some development best practices, some things we do as developers to ensure that the applications we're writing are able to take advantage of the scalable services and features that are on AWS, and then some operational best practices that we can use. I want to thank everybody for joining today. It was a pleasure being here. I'll look, and I think we have time to go over a couple of questions, and if you have any other questions, please go ahead and post them now. Otherwise, the video will be available after the conclusion of this webinar. So I want to thank everybody. Let's see.
Afternoon. Can everybody hear me? Yep, excellent. So my name's Tim Griesbach, and I'm here today to talk about designing resilient systems. And we're going to use the theme of failure is not an option.
Highly resilient AWS system. Related to that, this video
I know it's late in the
will guide
afternoon,
us.
so hopefully we'll get through this and everybody will learn some new stuff. Get the, well, there we go. So we're here to talk about building resilient systems and the trade-offs and risks that come with building those. First, we're going to walk through the question of what we're planning for. As part of this, we'll talk about what it means to be resilient, questions to think about when defining requirements for your system. Next, we're going to look at thinking resiliently. What do the nines mean? Different aspects of recovery and the shared responsibility. And then last, we'll get into some resilient system designs, talk about some patterns and blueprints, but it's more than just component architecture. You've got to think about things like testing and operations and how that helps you out there. So we'll start with this. Some of you may be thinking, I thought this was a session about when failure is not an option. And I know those of you who are AWS veterans will recognize this quote. This is Werner Vogels, our CTO, and what he often says, he'll say that everything fails all the time. And I know when I was a customer of AWS, that was one of the first things that I learned. And they really enforced that to me to think about how we build systems. And so his point is not that we must plan, is that we must plan for failure, not that we should accept failure. So we know things are going to fail. So the big question is, if failure is not an option for some of our systems, how do we address that? So first, let's think about resiliency. Let's maybe look at the definition of it. So it doesn't mean that nothing fails, it's quite the opposite. More importantly, what resiliency tells us is it's the ability to recover quickly and continue operating when a failure occurs. Keywords here being, you know you're going to have a failure, and can you recover when it occurs, not if. So what's driving this push for resiliency? As an SA, and I'm in the SA group for the federal civilian team, one of the things we're seeing is that as customers are looking at moving systems to the cloud, and it's causing kind of a reopening of questions and what we must expect from our systems. Many systems that we had on premise, they had exceptions in place or permissions, but now as they bring them to the cloud, folks are being asked to rethink, what is acceptable from resiliency. We see several themes driving that. I think first is one that'll hit home with a lot of people, is just a growing dependence on IT systems. Outages have a huge impact. You think about government services. Many of the government services that are now delivered through IT systems, if they're offline, that's a problem. Airline travel, you can imagine what happens there. Financial systems. I came out of the financial regulatory industry, and so if the systems go down there, it really creates some headaches. And then telecommunication networks, those are others. The second I put up here was reputation and legal. That's really driven by the first one. What does your company stand for? What is the agency, if you're with a government agency, what does that stand for, and what is your reputation? And then the last is monetary. So now we see more and more, and not just technical folks, but more and more business users who their day-to-day job is dependent upon IT systems. So if their system is down, they're idle, and that's lost opportunity cost. So then it's fun to think about, well, what are we planning for? We know that we're going to have failures. We've talked about that. We're being pushed to rethink things, but are all failures created alike, right? So we can start with this one, right? Is it spilled milk? Some failures, it's really, maybe a restoration, backup, restore, and you're good to go, right? And then there's others that is a little bit more impactful, larger scale event, talking about multiple resources maybe you've lost some servers within a system, maybe a network or routers down. And then you get to something like this, a larger scale event, where multiple people and resources can be impacted. Maybe a data center or multiple data centers are offline. If you all remember a hurricane that came through a number of years ago, came right through DC and right up to New York. And in some cases it took out both active and DR data centers for people. So as you can see, not all events are created the same. And I think we've got to take that into a balance. So then we must consider each of our applications and what their significance to our business is. What is the impact when a disruption occurs? What's the cost we're willing to invest? We can make things very highly resilient in the cloud. It just brings with it cost. Some of it's dollars, some of it's time, some of it may be performance. And ultimately, it's not a cookie cutter approach. So we're not going to have one answer that we can give you, and we can just say you can roll this out. So we're going to take this into account. So if we look at here, you see an example here of tier 1 to tier 4. Now I will say, we'll go out to talk to customers and they'll say, yeah, my email is tier 1. And then you start to try to understand, what is your business, what is the dependence your business has on that email? In some cases, it may really be actually tier 1. It shuts everything down when it goes down. In other cases, it creates some headaches, but business can continue. And so it's important to kind of balance those. And then you go all the way over to tier 4. And of course, you can see here, we've shown cost increasing, and cost goes up dramatically when you get into the tier 1 systems. All right, here's another one. So as the old saying goes, you only need to outrun your slowest friend, right? So what I like to say is that for systems nowadays are not just one thing. It's a complex kind of intertwining fabric of components put together. And in a way, you only have to the bear only has to get the weakest component in your system to bring it down in many cases. So we have to look at what are the possible things that can go wrong. So we'll walk through a few here. So one at the top is operator error. So for those who still have manual processes in your system, and I'm sure that's probably all of us, unfortunately, operator error is a very high probability of error occurring because it's dependent upon a human typing in something, and recovery from it's very challenging. You don't know exactly what was done. Those of you that worked in Unix boxes, maybe they logged in the wrong Unix box, maybe they used the wrong ID, they ran a command, now they got to figure out what did I do, how do I undo it? These things become huge problems. The next is deployment induced. So deployment is actually, I think we see that as one of the largest causes of failures in systems. When you go from dev to test to production, if you don't have, as you get a more advanced automated system, you're going to be better off. But a lot of times you're deploying something to production and somebody forgot to open a firewall rule, or they forgot to change something on one of the boxes that's running. Maybe some of the data's changed. And then as we move down the list here, we've got load induced. I think everyone's familiar with that. Data induced, I come out of a data environment, and I'll tell you, it's really, really hard to take into account all the variations in data. And there's some practices that are coming into place in testing today that help with that, but especially when you get into the big data systems where you've got billions of rows of data as an example, it's going to be, the variation is fairly dramatic. Credential expiration. If you've got, again, with these multiple component systems, you've got component A talking to component B, and all of a sudden the service account was expired. Quit working. Systems appear to be running, but there's kind of weird errors occurring, and maybe it's not all the time. And so you can see where these things create, some real headaches. And then we get to hardware and infrastructure. So we can't fix everything. Goes back to the Werner Vogel's quote, but we can be informed about it so that we can try to plan. And then it's always fun to think about the on-premise data center realities. We've all lived it, right? The traditional DR weekend tests. Everybody lived that? Yeah, it's a lot of fun. Well, it gets even more complex now when you've got hybrid systems. And you've got some systems in the cloud, some systems on-prem. And that's, as folks start taking advantage of the cloud, you're going to have a hybrid system for a while. So it's something important to think about. Internet external. Some of these are also just pointing out some of the challenges you deal with on-prem that are real anyway. So like people say, well, if I move to the cloud, I've got security issues. Well, if you've got a cloud and accessed application, oftentimes you're still going to have a lot of those even on-prem. So that's still important. The DR site's always active, so you're paying for it if you've got 2 physical data centers, having to deal with data replication, and then data security compliance. That's a fun one. Everybody gets to live that one. And some of these don't necessarily go away in the cloud. You just have to change how you do it. So we've talked about resiliency. We've asked the question about kind of severity of failures. We've looked at how to assess our system. So now I want to talk a little bit about what I've been saying, kind of think resiliently. We're going to change our thinking a little bit and talk about some of the principles. So for our 21st century application, some of you may have seen this. This is a great slide that talks about how our applications, we need to have test recovery procedures, and ideally they're all automated. We've designed to recover automatically. You'll notice the automatic words in here a lot. Scale horizontally to support increased load automatically. Recognize we can't guess capacity. So rather than trying to build for peak, you want to be able to scale up and down as needed. And at the end, all changes need to be automated. And that's actually a really important theme that'll come through here. So this is another interesting one. I don't know if anybody's ever actually thought about it or who thinks about it, but what do the nines actually mean? It's a little, when someone starts saying, well, you got to have 5 nines availability. These are big numbers. And the amount of outage time is very, very, very small. So if you just take 4 nines as an example, it's 5 minutes per month, 52 minutes a year, so it's about an hour. I've lived through outages, and generally speaking, an hour would be a pretty short outage when a system goes down on-prem. All of a sudden, you've blown your entire year's SLA, if that's what you're asked to do. So we really need to look at this and figure out what's important to our business, what's important to the customer, what's important to the users that are using the system, what's the impact, and then make sure we're picking something that's right and standing behind it. The cost goes up significantly as you go up, and there are systems that actually require this, so it's very important. So we'll talk about 2 other points here, and this is so in the kind of DR world, you think of RPO and RTO. So RPO is the recovery point objective. So this identifies where, if the system is kind of cooking along and a failure occurs, when you bring it back up, how far back is the data valid? Was there a eventual consistency going on where some of the data may not have been committed yet, things like that. And then RTO is when the failure occurs, how long does it take you to get the system back up and running, right? Now, of course, when we go ask everyone, they're going to say, well, I want both of these to be 0. I want to have all the data to be accurate the moment it failed, and I want the system to be able to come back up immediately. And what we like to do is really talk folks through, what is the system used for? What's the data behind the system? Sometimes it's more important that the data be valid. If you're an ATM machine, for example, and it goes down, you don't want, some of you might, the last withdrawal to not be committed. But then other folks are like, well, that's, maybe the data, the way the system is architected, what's more important is to get the system back up and running. And then at AWS, we believe in what we call a shared responsibility model. And so while we often talk about this with security, this also applies to resiliency. So we handle the infrastructure kind of from the hypervisor down. So the physical servers, the data centers, the power that's running them, and all of that. And it's that what we call undifferentiated heavy lifting, where we want to take care of that, and we'll provide that, and then in some of the cases, we've got some managed services. So you may think of that like an S3, for example. And so as you're using that, and then your responsibility is above that, which is the data, the security, again, the resiliency. What level of redundancy do you want to have in your system? So we've talked about resiliency, talked about classes of problems, the spilled milk, qualifying your applications, and some of the principles. So now let's start talking about how we would design resilient systems. So I find this to be a kind of a helpful law, the Gall's law, and that tells us that the complex systems will evolve from simple systems that work. So rather than trying to make a super complex system work, well, let's break it down into the pieces, and let's get those pieces working, and then let's build them up. You can also learn from the experience of Amazon and AWS. We started with the retail, the Amazon.com, and before AWS came along, there had been a lot of experience built into the scale and resiliency, and a lot of those principles then were carried forward into the AWS infrastructure and the services. And one of the things we tell ourselves internally a lot is there's no substitute for experience. And so we can go and learn, but sometimes you've got to have worked through things a few times, been through some failures and conditions. And AWS is really, there's no one that's been doing the cloud business longer than AWS. So we bring a lot to experience in some of the materials that we provide, the tools, the services, and even the AWS, the infrastructure itself. We'll show that in a minute. And then also on the operations side. So I think if you look at the way we've kind of architected the regions, the availability zones, the way the services are put together, what you'll see there is designs that are really built around having resilient systems. So let's talk a little bit about the AWS infrastructure. So we provide a reliable, scalable, low-cost platform. And today there's running thousands of businesses in 190 countries around the world. It's many folks are running in very high production, high resilient production systems. So it starts with a region. Each region is a separate geographic area where the cloud resources can be instantiated. Regions are isolated from each other, meaning that a disruption in one region doesn't impact another. And phrase you may have heard is contagion in that case. And this achieves the greatest possible fault tolerance and stability, the goal being that one region should not impact another. And regions are designed to be autonomous with dedicated copies of services deployed in each region. And then each region has multiple availability zones. Each availability zone has a collection of data centers in it, and they have very high connectivity between them, their own power and things of that nature. So what you end up with is kind of a base infrastructure that's capable of supporting highly resilient systems. And then on top of that is the services that we build. So if you think of S3, EC2, things like that, these are built in a very cell-based architecture. And the goal is that we want to make sure that if there's a failure, the blast radius is very small. Because again, things are going to break. And you have to plan for that. We actually use our own services internally for the things that we build and deploy. And I think the other thing is just to think about distributed systems and how you build, you've all heard microservices. So as you go to a more cloud native architecture, you're going to want to start building things that are very microservice based. In some cases it's maybe server based, in some cases you may move to more serverless as function as a service. Then we can look at where we have regions around the world. So to enable recovery across the globe, it's necessary to ensure that the network supporting your applications is appropriately redundant. It's always available and seamlessly routed. So if you're going to build a resilient application, but everything underneath of it's not resilient, you're going to have a challenge. So we provide a global infrastructure with 21 regions and 64 AZs, or availability zones. We've announced plans for 12 more availability zones and 4 more regions. There include Bahrain, Indonesia, Italy, and South Africa. And so for app designers, we kind of say this is akin to having multiple data centers across the globe where an application can be hosted. So we move on to the next one, and we kind of show how they're all connected. So you can have lots of regions and lots of data centers, but if they don't have very good connectivity, you're going to have some equal challenges there. So we provide global connectivity options with Direct Connect network of 94 locations around the world. So the global network of AWS points of presence, which are the edge locations and regional edge caches. There's 169 POPs today in 68 cities across, I think it's 29 countries. So think like United States, Canada, Europe, Africa, Asia, Australia, and South America. All the continents excluding Antarctica. Oops. Sorry about that. So if you've got resilient infrastructure, resilient networking, now you've got to have resilient data, right? So if you can't trust your data, it really doesn't, again, it won't matter if the other pieces are resilient. Can you all still hear me? I know I dropped my. So we provide a number of services and infrastructure for you to ensure you have resilient data. So we think of, there's file systems, block storage, which is like EBS. You've got object store like S3 or Dynamo, databases, RDS, in-memory caches. But the idea is that we are going to provide enough components and tools for you to build the system that meets your needs. So we're not going to give one thing and say you've got to put everything into that. So you're going to have the flexibility to design resiliency that meets your needs. And so this diagram here is just one example of how, if you're using, say, RDS, and how you need it to work across multiple regions, how that might work. And it relies on various replication and read replicas and things of that nature, but you can do it. And you may have trade-offs, you may have some latency, or you may have something maybe read-only in an alternate region that you then have to turn on later. We've also got, there's other features. You think of things like cross-region replication, cross-region replicas of snapshots, storage and file gateway, DMS, DynamoDB global tables. So there's quite a few different capabilities that are available to use in the toolbox to ensure you've got resilient data. There we go. All right, so we've got infrastructure, networking, data, and now it's our applications. So we're kind of working our way up here. So you can have all these things in place, but if your application is not self-healing, as we like to call it, then, for example, an auto-scaling group is not going to help you a whole lot. System goes down, we start up another one, but if you had lost state, for example, you're going to have challenges. So the key is to then start thinking about our application, making sure it's self-healing. So they ought to be able to monitor and recover. That's important. So in this example here, so if you think about this as a set of microservices, so we've decoupled them, so try to remove dependencies, we've removed state, so that now you've got an ELB, and if there's a failure, the auto-scaling group can start up another one, and the traffic continues operating. So eventually this also turns into, if you go to look at a serverless picture, it's even in some cases simpler than this, because you're relying on the AWS infrastructure for that undifferentiated heavy lifting to deal with the infrastructure, and you're just making sure that you've got your function there and the ALB in front of it through, say, API gateway that can run it. All right. What are we doing here on time? So now we've laid the foundation of infrastructure, networking, data, self-healing applications. Now we can actually think about some blueprints for system designs. We're going to cover this at a high level. Again, and I'm going to share with you some resources at the end that if you really want to start diving super deep, that'll be good for you to look at. And then also the SA. So I come from the SA community. We love to work with the customers. That's our goal. So to understand your needs and requirements and then help you map something out. So let's start with the first one. This is a, kind of following that Gall's law, right? We're going to start simple. And this would be the single region multi-AZ. Now, hopefully, this is where folks start when they go to the cloud. But it depends on if they're building a kind of a cloud native app or if they're moving something in that's capable of running in multiple AZs. But this is a great start. We've got many services that are many of our services are kind of region wide, so we guarantee the availability of the service and the content. So if you think of like S3, for example. And so with this you can leverage, so some of my lists up there is S3, DynamoDB, EFS, SQS. But it's this con that gets the question. That is, if you are being pressed for resiliency greater than 99.9%, that's when we need to start thinking about multi-regions. But I would still start here, because this is going to be the foundation for the next slides that we're going to get into. So we call this resiliency within a region. Then you can go to the next step, which would be taking what you had before and now thinking about doing it as, looks a little bit more like what you may have traditional DR world, where using multiple regions, you've got an active and then a passive that's waiting to be, or standby that's waiting to be brought online. So it more closely looks like your traditional pattern. The challenge here would be that if the active goes down, bringing up the standby, maybe that's hours. It depends on what you have in the system. Do you need to resync things, some things like that. So there's kind of a hybrid of this that we call pilot light. And so if you needed to get an RTO of less than 4 hours, maybe you were in the 15 to 30 minute range, maybe you would consider using a pilot light, where you had part of it running in the alternate region and you were monitoring it and making sure it was ready, but you didn't have the full system running in that region. And then this is really the holy grail. I mean, this is the multi-region active. Looks like we've got a visitor. Oh, y'all can't hear that probably. It's an airplane flying over. So this is where, for systems with the highest requirements for availability, we see customers starting to look at multi-region active patterns. And this involves a lot of thinking. You're going to have to use multiple stacks running in multiple regions. You're going to have data replication occurring in real time. You're going to have to think about what your RPO needs to be. You may even start thinking about things like eventual consistency, so that as data's transactions are applied, are they instantaneously applied across multiple regions, or are they propagated? And each of those things carry costs in performance, costs in dollars, complexity of the system. Latency is probably the big one, the challenge here. There's also some storage layer replication technologies. I mentioned up here some APM partners. So you think of, there's Cloud Endure, disaster recovery, Attunity Replicate, Randisco Fusion, NetApp, Cloud Sync. There's a number of technology you can use, because if you need to be able to replicate at the disk layer, there are services out there that you can use for that. And then this last option, this is kind of an interesting one. We're going to call this multi-region dual write. So this would be a case where you've got a legacy system. You may not have a lot of control on the internals of it, but you need to try to, is there a way we can make it highly available across multiple regions? So what you're going to rely on here is you're going to effectively have two stacks running independently of each other, and then you're going to build some services around it, which would deal with replication. But now you have to start thinking about things like checkpoints. You've got to make sure these two systems are in sync. So some of them may be things that run real time. Some of them may be you run something every night that goes through and checks data, files, things of that nature. But there are cases where this is a viable option. Not ideal. But these, again, trying to put out here what are the options you can use. Safeguards is the big one. Let's see what else we got up there. And again, little to no change in apps. And usually that's because you can't change the app, not because you don't want to. That would be an anti-pattern. So we've covered a lot in those 4 patterns. But I think it's also good to think about what are some of the kind of anti-patterns. What are the things we're trying to avoid doing, right? Sometimes people will try to they'll put a heavy focus on making individual components very, very reliable, versus recognizing that things are going to fail and making things work so that they can be run in parallel. You can have multiple instances. Continuing to trust in manual process and operations. I know we all have gotten comfortable over the years with our processes that we run on premise. But it's a great opportunity, especially with infrastructure as code and the automation capabilities as we move to the cloud, to re-ask that question. Is there a better way? So we've got a few here. The replicating on-premise ones, the use of non-redundant architectures, single data center. So sometimes, and they'll end up with what looks like an on-prem data center in the cloud. I would call that an anti-pattern. Reusing manual processes. Now this last one, assuming data is safe in your data center. The irony in that is that the on-prem data center will oftentimes, there'll be a perception that the data is really safe in there. And so we had, and went through that when I was at a customer, where you all of a sudden realized there was some challenges, and we went and had to encrypt everything, even on-prem, which was the right thing to do. But it was a lot of work and it caused a lot of change. But a lot of times there's that perception that it's my data center, I own it, I control the processes to access it. And then but people go to the cloud, I think there's more of an awakening to realize that's not a good idea, and looking at trying to make it more secure. So really it's this: don't sacrifice long-term value for short-term results. Oftentimes, I've spent a lot of years writing software and working in IT, and it feels like that's oftentimes what it comes down to. We're all faced with budgets and project deadlines, and we're a lot of pressure to try to get those things done. And these decisions that we make, we're going to have to live with, possibly for years. So if you've got a chance now to rethink it and make sure that the folks that are part of that decision-making responsibility, that they are aware of what are the trade-offs, and really encourage folks to think about it now and assess that, even if it means maybe moving a date out or possibly de-investing in one area and putting more investment somewhere else to make sure it's right. All right, so we've talked about infrastructure, data, apps, and some architectures. But this is another one that's kind of interesting: operations. You can have a resilient, web application. You can have systems that are auto-scaling. But if your operations, if you haven't gone through and thought about how we're going to make our operations resilient, you still have a fairly significant gap that could be a problem. So we can't overlook that. This goes back to the slowest guy and the bear. It's important to make sure that we are thinking about everything. Excuse me. So here on this one we're talking about, the best design require operational excellence to ensure high availability, mitigate downtime, and to compensate for limitations in our design. So if we think about the operations focus of resiliency in the cloud, the goal there is on the successful implementation of change, execution of processes. Do we know what the operational health of our system is? Timely and effective responses to events. So we can know an event occurred, an alert can go off, but if nobody is there to respond to it, is it any good? So some of the key things we've kind of got outlined here is operations as code. That changes everything. Ideally, you should try to get to a point where you've got zero manual touch on things when it comes to, say, deployments and operations. Everything is automated. In one of the projects I was working on when we first came to the cloud, when I was back at a customer, we made a decision early on that no one could log into an EC2 box. Now, for those of you that are, the Java programmers and the, system admins, we all fought it. I mean, they were all like, oh, we can't do that. But the reality is, excuse me, it causes you to change thinking, adopt new processes and tools, and eventually you'll get there to where it actually is valuable. And then all of a sudden you're at the point where you don't look back and everyone really values it. Documentation, frequent small reversible changes. So this is another one you all have probably heard this talked about, where if you deploy something and there's 5 changes in what you've deployed and something breaks, it's going to be a lot easier to figure out what broke than if you've deployed something that's got 1,000 changes in it. And so you want to make small frequent changes. Anticipate failure, learn from operational failures. So these are the kind of things on the operational side that are very important. So at AWS, one of the lessons we've learned is to automate everything. And again, that's really, that would be one thing that everyone ought to take home. So as Werner up here says, a key mechanism to achieve this is to automate the management as much as possible, removing error-prone manual operations. And the cloud makes that possible with the configuration as code, with the APIs that have laid out there, so as you all start to adopt it. So if you've architected with resiliency in mind, a recovery environment, for example, can be stood up in minutes via AWS CloudFormation templates or AWS Systems Manager automation. Another thought here was that a lot of organizations are great at monitoring, but they're not so good at acting on them. What do? Do you have Do you just set an alarm, or have you actually built automated responses? So if you sense that a system is not doing well, what are you going to do about it? And can you programmatically respond? And a lot of that can be done now. And we've seen cases where customers doing that. And then application deployment. So I think we mentioned earlier, so application deployment is one of the most common causes of failure. And it's not just the deployment, but it's the setup of all the environment that goes with it. Because you're not, if you forgot to propagate a change from a lower environment up type thing. So in this case, on AWS, using infrastructure as code, you can integrate the infrastructure changes, application changes to be tested, and validate before they reach production. I'd suggest thinking about things like blue-green or canary deployments. So these are part of that, what you may have heard of CI/CD. So with blue-green, you stand up a new environment, make sure it's working, and then you switch over to it. With canary, you might start rolling out changes to a few servers, make sure it's good, and then keep pushing it out. And a lot of these, again, going back to the slide, we're talking about lessons learned from AWS. These are all things that we do internally with our services across AWS and Amazon.com. So we've got developer tools, including, so there's AWS Code Commit, Code Build, AWS Code Deploy, Code Pipeline. These are all designed to provide that integrated set of tools which allow you to build pipelines integrating infrastructure and code deployments. And they're configurable, and they allow you to factor in some of these deployment techniques that we've talked about. All right, so now we've thought about resiliency, we've talked about our application requirements, we've picked a platform, AWS, we've designed our application operations. What about testing? Testing's another big one. So I like to say testing enforces resiliency if you're doing the testing right. I don't know how many saw this at reInvent a couple years ago, but remember, think about chaos engineering, those of you that are familiar with it. So this line is perfect right here. Chaos doesn't cause problems, it simply reveals them. Those problems were there, you just haven't been brought to light yet. So utilizing the principles of chaos engineering, you can incorporate that into your testing and your development processes to actually find these things earlier on. So we're going to leverage this to ensure our resilient systems continue to operate. First, we've got to have a detailed understanding of the failures and impacts on the system. So the test scenarios and plans that you have, they should actually be based on a careful study of what are the failure modes of your application. So there's a practice here that's referenced called failure mode effect analysis. Some of you may have used this. But it uses a technique where users get empirical measurements and they actually go through the different failure modes and what are the effects. And your goal is to try to keep reducing it down to the point where you've got a more stable system. But this is now we're going to go with chaos. Up to this point, we've talked about just the testing scenarios. But how do we actually, if we just think about single failures, when we've got, remember, most of our systems now are multiple components. So we can't, it's not just good enough to make sure that one component's working, but what happens when a component in a complex system goes down? And oftentimes when that occurs, it's not even obvious that there's an error. You got weird conditions start occurring. It's not necessarily that people can't even log into the system. So today's apps are built on new platforms. You've got web, you've got mobile, IoT, distributed technologies. And even when each individual service is distributed and functioning properly, the interactions between them, that's what we were talking about. So how would it behave if there were multiple failures? So some of you are familiar with, if you've studied chaos engineering, the idea is that it actually goes out and starts introducing chaos into your system. And the goal would be to identify, what happens if a server goes down? What happens if a router goes offline? What happens if a user ID or a login is disabled? And why don't we actually make that part of our regular development testing environment so that we're seeing it? And then you can really take it to the next level. And if you've heard Netflix talk about this, right, you actually can do this in production. And I know it sounds, the first time I heard that, I thought, that seems a little bit, I'll stick to development and test. But we actually incorporated it when I was, before I came to AWS, and we had it running really well in lower environments and eventually moved it into production. And you can, you pick and choose what you're going to start with. You dip your toe in at first. But eventually it starts identifying problems in the system and it becomes super resilient because of that. And this is, everybody's probably familiar with Chaos Monkey and the Simian Army. So now they've got a whole number of tools that can deal with servers, regions, different pieces of things, even slowing traffic down, things of that nature. So this is something that is worth capturing and you incorporating into your environment. All right. And ultimately, your goal is to make a continuous testing environment. Make it part of what you do. Make it part of your development. So that you aren't just building stuff and then throwing it over the wall of the test team and then coming back. And this is, I love this slide here. This is, we're builders, right? And I think everyone here is builders. And so our goal is to recognize that this is not a cookie cutter approach. So we as SAs, we love working with the customers. We want to understand what are your needs, what are your gaps, what are your challenges, and help you try to figure out how you can kind of define the best resilient system that's going to work for your customers. I don't have a... So now we're going to wrap up with a couple of items. I want to talk about some future considerations as you move to the cloud. First is really going serverless. So I think that if you're maintaining things like AMIs, ideally you want to get to a point where you no longer have to maintain AMIs. You want to worry about building your business logic, building your business services, doing things that are going to add value. So going serverless is a big plus here. Leveraging the AWS region-wide services, breaking it down into smaller services. You want to reduce the blast radius. So when something fails, you want to make sure that what fails has a small impact and that you're able to recover quickly. And then the well-architected tool that's here. So some of you may be familiar with our well-architected process, and I'll share a link on that in a second as well. And last year at reInvent, we announced the well-architected tool, and that allows you as the customer to go out and you can actually go through and do an assessment of a system and your processes, and it goes through all the 5 pillars. So you can, assuming you answer the questions, what level of detail you choose to provide it, it'll then provide information back on how to make things better. And kind of in closing, I just wanted to share some additional resources. Again, as I had said earlier, we're going to kind of stick high level, kind of go end to end on this. But I would really recommend folks the well-architected framework. There's some great material that we've got published online about that. So folks should take some time and read through that. We published a white paper earlier this year, and this really came out of the financial services space, but it applies, it's much broader than that for around mission critical financial service applications in AWS. So that's available. And then these 2 reInvent presentations over the past couple of years. These take a real deep dive into multi-region deployments and architectures, and looking at things like latency and some very low-level stuff. So it's really interesting that they go deep into that, and you can kind of see that. And then the last is just making sure you're building the microservice architectures. I thought this is it's really important to understand this is a big part of being able to eventually get to highly resilient systems in the cloud, are breaking down these big applications into smaller pieces that are running in the cloud. All right, and I think that
So here all the details related to theoretical part of like this designing the elastic and highly available resilient infrastructure for varied application scenarios on AWS. This part is been covered. Okay. detailed notes I will provide to you, which will cover all the theoretical part. Means, suppose for example, if you are having theory paper on this, then it will be helpful for you. So the that kind of a theory notes I will definitely provide to you. Still we are having some time, so let us discuss. Means, in last lecture, whatever that we have seen about the basic compute, storage, networking and IAM services of AWS, Microsoft Azure and Google Cloud platform. So the basic difference with all these points that I will share with you. Just give me 1 minute. Just give me 1 more minute for the same. Yeah. Mhm. Okay. So you might be asked the question like, what is the difference between these three? So that part I will share with you. Google Meet. Yeah. Okay. So see the difference between these three. So this kind of a question can be asked in our exam. So the difference, like Google Cloud, so it uses GCE, that is Google Compute Engine, for computing purposes. So all the details, how it works and all. So that part already we have covered. So GCE, very important structure in the Google Cloud. Then in case of AWS, AWS EC2 offers core compute services. And in case of Azure, it uses virtual machines for computation purposes. So VMs are important in case of Azure. Again, in case of a Google Cloud, it uses Google Cloud Storage for storage purposes, as we are already using this Google Cloud or the facilities provided by Google to us. Then in case of AWS, it uses Amazon S3 for storing the data. And in case of Azure, it uses a storage block, Bob, that comprises blocks for storing the data. So how it works and the details already we have covered. We are just now discussing the differences. Again, Google Cloud, it offers the lowest price to the customers to beat other cloud providers. As we already know that Google is on the top, it is providing all the facilities to us. So definitely many of the users are turning themselves towards the Google Cloud only. So why this reason is because it is offering the lower price. That's why. In case of AWS pricing is generally keen to have inscrutable. The overall structure of granular pricing is a bit complex. And in case of Azure, so like AWS, Azure pricing structure is also difficult to understand unless you have considerable experience. So this is the point related to how to store the data and all. Then Google Cloud, it uses cloud test labs for app testing purposes. In case of AWS, it uses a device farm for app testing purposes, and Azure, it uses dev test labs for app testing purposes. Google Cloud, it uses the subnet as a virtual network. Then in AWS, it uses VPC, virtual private network, virtual network. And in case of Azure, it uses VNet as a virtual network. Then Google Cloud, it follows the cloud load balancing configuration. AWS, it follows the elastic load balancing configuration, and Azure, it follows the load balancer application gateway configuration. So this is the difference between these three. Then if the question related to this, if it is asked, you can answer with this particular difference point or this particular table. Okay, so it's 11:30 now, so we will stop here, and the next part of this chapter, and that is nothing but, let me see. Yes, so whatever we have seen for designing elastic, highly available, resilient infrastructure for varied application scenarios, so that part we will cover for Microsoft Azure in our next lecture, and then after for Google Cloud Platform also. And then we will go for the financial technological implications of running an application on a public cloud. So these two bits of this chapter are remaining. So I think our unit test dates are not yet declared, right? Or are they declared? From when you are having your ISC?
No, ma'am, we don't know.
Okay, then that will be fine. So I will try to finish our this third unit before ISC, so that all the three chapters, means 1, 2, 3 units will be there for your ISC. Okay, related notes definitely I will share with you. Many of the students are asking for the same, but little bit means they are ready with me, but some kind of alignment and the fonting and that kind of things are remaining from my side. So whenever I will complete it, I will send it to you. I will try to send all the three together, means collectively, so that it will be helpful for you. Otherwise I will share it one or first chapter now, then again the chat window will means our WhatsApp, that will increase the length. Then again student ask me about where are the first chapter notes, like that. So before IIC, I will send all the three chapters collectively with you. Okay, so I think we will stop over here, and okay, fine. So put your attendance in the chat window, and then you can have your lunch break. Okay, thank you very much. Tajmin Bhagwan, put your attendance and leave. You are the only person remaining over here. Tajmin. Okay, so I will stop the recording over here. Thank you.